In mathematics, an elliptic curve is a plane algebraic curve defined by an equation of the form that is non-singular, that is, its graph has no cusps or self-intersections. Formally, an elliptic curve is a smooth projective algebraic curve of genus 1, on which there is a specified point O. An elliptic curve is in fact an abelian variety, that is, it has a multiplication defined algebraically, with respect to which it is a group, and O serves as the identity element. Often the curve itself, without O specified, is called an elliptic curve. The point O is actually the point at infinity in the projective plane. If y2 equals p, where p is any polynomial of degree 3 in X with no repeated roots, then we obtain a non-singular plane curve of genus 1, which is thus an elliptic curve. If p has degree 4 and is square-free, this equation again describes a plane curve of genus 1, however, it has no natural choice of identity element. More generally, any algebraic curve of genus 1, for example from the intersection of two quadric surfaces embedded in three-dimensional projective space, is called an elliptic curve, provided that it has at least one rational point to act as the identity. Using the theory of elliptic functions, it can be shown that elliptic curves defined over the complex numbers correspond to embeddings of the torus into the complex projective plane. The torus is also an abelian group, and in fact this correspondence is also a group isomorphism. Elliptic curves are especially important in number theory, and constitute a major area of current research. For example, they were used in the proof, by Andrew Wiles, of Fermat's last theorem. They also find applications in elliptic curve cryptography and integer factorization. An elliptic curve is not an ellipse. See elliptic integral for the origin of the term. Topologically, a complex elliptic curve is a torus. Elliptic curves over the real numbers. Although the formal definition of an elliptic curve is fairly technical and requires some background in algebraic geometry, it is possible to describe some features of elliptic curves over the real numbers using only high school algebra and geometry. In this context, an elliptic curve is a plane curve defined by an equation of the form where A and B are real numbers. This type of equation is called a Weierstrass equation. The definition of elliptic curve also requires that the curve be non-singular. Geometrically, this means that the graph has no cusps, self-intersections, or isolated points. Algebraically, this involves calculating the discriminant. The curve is non-singular if and only if the discriminant is not equal to 0. The graph of a non-singular curve has two components if its discriminant is positive, and one component if it is negative. For example, in the graphs shown in figure to the right, the discriminant in the first case is 64, and in the second case is minus 368. The group law. When working in the projective plane, we can define a group structure on any smooth cubic curve. In Weierstrass normal form, such a curve will have an additional point at infinity, O, at the homogeneous coordinates O, 1, O, which serves as the identity of the group. Since the curve is symmetrical about the x-axis, given any point P, we can take P to be the point opposite it. We take O to be just O. If P and Q are 2 points on the curve, then we can uniquely describe a third point, P plus Q, in the following way. First, draw the line between P and Q. This will generally intersect the cubic at a third point. We then take P plus Q to be R, the point opposite R. This definition for addition works except in a few special cases related to the point at infinity and intersection multiplicity. The first is when one of the points is O. Here, we define P plus O equals P equals O plus P, making O the identity of the group. Next, if P and Q are opposites of each other, we define P plus Q equals O. Lastly, P equals Q, we only have one point, and we can't define the line between them. In this case, we use the tangent line to the curve at this point as our line. In most cases, the tangent will intersect a second point R and we can take its opposite. However, if P happens to be an inflection point, we take R to be P itself, and P plus P is simply the point opposite itself. For a cubic curve not in Weierstrass normal form, we can still define a group structure by designating one of its 9 inflection points as the identity O. In the projective plane, each line will intersect a cubic at 3 points when accounting for multiplicity. For a point P, P is defined as the unique third point passing through O and P. Then, for any P and Q, P plus Q is defined as R, where R is the unique third point on the line containing P and Q. Let K be a field over which the curve is defined and denote the curve by E. Then the K rational points are the points on E whose coordinates all lie in K, including the point at infinity. The set of K rational points is denoted by E. It, too, forms a group, because properties of polynomial equations show that if P is in E, then minus P is also in E, and if 2 of P, Q, and R are in E, then so is the third. Additionally, if K is a subfield of L, then E is a subgroup of E. The above group can be described algebraically as well as geometrically. Given the curve y2 equals x3 minus px minus q over the field K, and points p equals and q equals on the curve, assume first that x p x q. Let S be the slope of the line containing P and Q, i.e., since K is a field, S is well defined. Then we can define R equals P plus Q equals by if XP equals XQ, then there are two options. If YP equals minus YQ, including the case where YP equals YQ equals 0, then the sum is defined as 0. Thus, the inverse of each point on the curve is found by reflecting it across the x-axis. If Yp equals Yq0, then R equals P plus P equals 2P equals is given by associativity. All of the group laws except associativity follow immediately from the geometrical definition of the group operation. This animation illustrates geometrically the associativity law. Notice that the sum of the 3 values on any of the 6 lines is 0. The location of all 9 points is determined by the elliptic curve together with the locations of 0, A, B and C. The central point of the 9 lies on the line through A and B plus C, and also on the line through A plus B and C. Associativity of the addition law is equivalent to the fact that the curve passes through the central point in the grid. From this fact, the equality of minus and minus plus C follows. This idea can be formalized using the Cayley-Bacharach theorem. The elliptic curve and the point 0 are fixed in this animation while A, B and C move independently of each other. Elliptic curves over the complex numbers. The formulation of elliptic curves as the embedding of a torus in the complex projective plane follows naturally from a curious property of Weierstrass's elliptic functions. These functions and their first derivative are related by the formula here. G2 and G3 are constants, is the Weierstrass elliptic function and its derivative. It should be clear that this relation is in the form of an elliptic curve. The Weierstrass functions are doubly periodic, that is, they are periodic with respect to a lattice lambda, in essence. The Weierstrass functions are naturally defined on a torus T equals C lambda. This torus may be embedded in the complex projective plane by means of the map. This map is a group isomorphism, carrying the natural group structure of the torus into the projective plane. It is also an isomorphism of Riemann surfaces, so topologically, a given elliptic curve looks like a torus. If the lattice lambda is related by multiplication by a non-zero complex number C to a lattice C lambda, then the corresponding curves are isomorphic. Isomorphism classes of elliptic curves are specified by the J invariant. The isomorphism classes can be understood in a simpler way as well. The constants G2 and G3, called the modular invariants, are uniquely determined by the lattice, that is, by the structure of the torus. However, the complex numbers form the splitting field for polynomials with real coefficients. And so the elliptic curve may be written as one finds that, and so that the modular discriminant is here. Lambda is sometimes called the modular lambda function. Note that the uniformization theorem implies that every compact Riemann surface a genus 1 can be represented as a torus. This also allows an easy understanding of the torsion points on an elliptic curve. If the lattice lambda is spanned by the fundamental periods omega-1 and omega-2, then the n torsion points are the points of the form for A and B integers in the range from 0 to n-1. Over the complex numbers, every elliptic curve has 9 inflection points. Every line through 2 of these points also passes through a third inflection point. The 9 points and 12 lines formed in this way form a realization of the Hess configuration.